last time. We're finishing off the story of how could it possibly be the case that you can prove, like we've already had this instance of how could it be that you can prove that something's not constructible, right? There's no possible operation which will allow you to trisect an arbitrary angle. Fine. But how do you prove that that an axiom is necessary, right? That's like a whole other level of seeming impossibility. How do you prove that something's not provable? So this is the beauty of what Beltrami did, and we started talking about this, right? So Euclid's geometry. Let me write in English. Euclid's geometry is synthetic, or at least it aims to be synthetic. That is axiomatic. He declares, or what he should do is declare things to, again, there are points and lines and planes, and those things are undefined terms. Points, lines, and planes, at least in theory, should be, or are undefined terms. And then the postulates say what you can do with them. The postulates say what you can do with them, like P1 says any two points determine a line, etc. Right? This makes sense? Can you guys see this? And so what Beltrami comes along and finally says, so this is, anybody know the year? I think I know. 1868, very good. So Eugenio Beltrami, Italian mathematician, says, sounds like salami. Beltrami, salami. I see the resemblance. There's a poem in there somewhere. A slice of salami will be very relevant too, because it's a disc. So we'll get to the Beltrami disc in a second. Realizes he finally, I mean, in retrospect, it's like, how could people not have realized this before? But he realizes the importance of models, the role of models in showing that the parallel postulate P5 cannot be proved from the other four. And here's how. Actually, so this is a game. Does anybody play this game? You know what this is? You played this? So how do you play?
One matching object between the two cards. And
yes.
Play whoever finds the match first.
Exactly. Exactly right. So there's a variety of ways of playing this. Let's see. How do I oh, I could just stop share. Can you see the cards now? Now we're going to get that infinite feedback. Okay, how about that? So here's a card. Every card has on it, let me stand over here so I can see. Every card has, no, I have to look over there. Has on it like, what is that? Ladybug, treble clef, a zebra, a lightning, a maple leaf, yin, yang, and a tree. And what is that? Splot of ink. Okay. And here's, I just grabbed two cards at random. Here's another card. It's got a clock. It's got fire. It's got a candle. It's got a bullseye. It's got a question mark. It's got a treble clef. It's got an apple, and it's got a dog. So what do you notice? The treble clef, these two have a treble clef in common. Okay, I'm just going to grab two more. Ready? The second you see what they have in common, shout it out. That's how you win a point. Clock. Jemima gets a point. Here's two more. Very good. You've had practice. Okay, so Marley's not allowed to play because she's had practice. Yeah, the cactus. You see the cactus on both cards? One more. Two points for Jemima. The clown there and the clown there. Okay, so this is a little tricky. It's a fun little game to play. And then, so this was actually a gift to my older son when my younger one was born by a friend. I'd never played this game before. And I immediately saw what was going on and had to confiscate this for a full analysis. And poor guy's never actually gotten really to play with it. I do have to give it back to him at some point. But so what's actually going on? What's going on? So let's think about what's happening in Spot It. This game is called Spot It. So what's happening in Spot It? Yeah, it's a great game.
Good for road trips.
Good for road trips. Yeah. Yeah. There's lots of different versions. Like everyone can get a card and then you pick one up and you hold it, and everybody is going to have exactly one thing in common. Whoever shouts it out first gets a point or something. So what's happening in Spot It? Every single card, every pair of cards, has exactly one, what are these called? Images? Icons, has exactly one icon in common. And it turns out that Spot It is not perfectly made. There are 55 cards. I'm not going to show you. I guess I have to show you. Right there, it says it has 55 cards. It should actually have 57 cards. There are 2 more cards that you can make. This is a fun little, if you ever want to figure out this stupid game, there's 2 more cards that you can add that will, so that the game, it should satisfy the following property, should satisfy that every pair of icons appear on a unique card. Why am I showing you this game? What does this have to do with, what does any of this have to do with what we've been talking about?
It's a model for something.
Yes, a model for. Exactly right, Layla. Jemima.
Talking about how every a point has.
Yes. Yes, any 2 points determine a line. So you can think of cards as points, right? Look at P1. Any 2 points determine a line, because there's a line that connects those 2 points. Any 2 distinct points, I should say, determine a line. So Spot It is a model for, it turns out, projective geometry. Projective geometry. It's a finite projective geometry. It's a finite projective geometry. In the same way, remember we looked at the sphere, right? On a sphere, on the surface of a sphere, any 2 lines determine a point, where lines mean great circles and point means pair of antipodal points. And any 2 points, if I have 2 distinct points, so one point might be this pair of antipodal points, and another point might be, I don't know, that pair of antipodal points. And any 2 points determine a unique, those 4 points on the surface of a sphere that are two pairs of antipodal points determine a unique line through them. So projective geometry, this is what we saw as spherical projective geometry, continuous projective geometry, the projective plane. Spot It is a finite projective plane and has this structure that there's exactly one icon in common. So this is an instance of a model. What's the model? We can say that the plane is the whole game. A card, actually, there's a duality between points and lines. So we can be agnostic about what lines and points mean. You can think of a line is an icon and a point is a card. And so an icon being on a card means that point lies on the line. Or you can think about it, or alternatively, you can think about it the other way. Maybe it's somehow more natural. You think of lines as having lots of points, as opposed to thinking of the set of cards that contain an icon. So a line could just as well be the card, and the point could be the icons on the card. So which icons lie on which card tell you which points lie on which lines, and vice versa. Okay, so just to show you that there's an abstraction, there's a much more abstract thing going on here, where if you are allowed to have undefined terms, point, line, and plane, then you can see all kinds of really cool structures happening elsewhere. Okay, does that make sense? Does that make some sense? So here's what Beltrami discovers. He discovers, yes. So I was just showing you an instance of postulate 1. Projective geometry actually has slightly different postulates from Euclidean geometry. In Euclidean geometry, there's such a thing as parallel lines. In projective geometry, every single pair of lines intersects somewhere. And so that's what's going on the surface of a sphere. There are no parallel lines. And that's also what's going on in spotted. There are no parallel lines. Every pair of lines, every pair of cards has exactly one icon in common. Is that cool? So this is like a very deep. I don't think the creators of this had any reason to. They were just doing something combinatorial. They thought it was a fun game, and they discovered, perhaps, I don't know who made it. Cool. So here's what Beltrami discovers. So let me explain what Beltrami discovers. Beltrami makes a model for that other kind of geometry that we were talking about with Bolyai and Gauss and Lobachevsky. By the way, it's kind of funny. I mean, the book tells the story this way, so I tell the story this way. But there's a completely different way to tell the story of what happened, right? In Russia, there's a young guy named Lobachevsky, and he publishes his thing. And then a few years later, he hears about these two other idiots in Europe, Gauss and Bolyai, arguing about who was there first. He's like, guys, I was there first. End of story. I published it. I wrote it all out. What are we talking about? So I just want you to be like, anytime I tell a story, understand that I'm telling a story from the point of view that I know the story. And there are other viewpoints on this thing. So already we're experiencing that. There was a discovery I read yesterday that they discovered a new Mayan city. That there was like a grad student who was using, I think, LiDAR. There were like LiDAR maps in South America, and they were like, it's 15 kilometers from lots of civilization, and nobody thought to go over there. Nargis?
Actually, really interesting. Right. Obsession, but they use like scanning of some
Yeah.
geometries, but they basically use like geometry to note like unusual like geographical formations that
Yeah.
could possibly be cities, because a lot of them are so far buried that the only thing left is like a big hill.
Yeah. Yeah.
So,
And you have to look under the vegetation. Yeah. And so anyway, so maybe we'll know a whole lot more about Mayan math in a few years. And I thought it was a pretty cool thing. So what does Beltrami discover? A model for the geometry, this weird geometry hinted discovered, I guess we should say, not just hinted, but they really proved a whole lot of theorems, discovered by Lobachevsky and Bolyai. And we should put Gauss in there, although Gauss doesn't really deserve the credit, having not published anything. We do know that he discovered a bunch of things. What's the model? So to explain the model, let me tell you what the model is. And in fact, I won't tell you Beltrami's model. I'll tell you Poincare's model, which has Poincare in 1882 gave a slightly different version. And that's the one that I'll show you, and you'll see in a second why that's the one that I'm showing you. So Beltrami's model lives in a disk. So by plane, and so does Poincare's. The plane will be a disk. Okay, so everything lives in a disk. You wanted salami for Beltrami, take a slice of salami, and that's where everything exists. Okay, so we have a disk, and Beltrami's model had straight lines going through. Poincare gave a slightly different version of the model, but by a line in this model will be a circular arc orthogonal to the boundary. A point will be a point in the disk. A point is point in the disk. And a line in this Poincare model, which is a slight tweaking of Beltrami's model, is a circular arc orthogonal to the boundary. Okay, so let's check some of the axioms. P1 says between any 2 points, so here's a point and here's another point, can I draw a circular arc? Does there exist a circular arc that's orthogonal to the boundary through these 2 points? The fact that you can draw, so let me just say, draw line segment, of course, segment between 2 points. Okay, the fact that you can draw a line segment between these 2 points with straight edge and compass is a theorem of Apollonius. We haven't really talked about Apollonius Narvis. Orthogonal means that they meet at right angles. So if you zoom way in, even though they're arcs of circles, if you zoom way in on an arc of a circle, I can't zoom far enough, but they'll look like straight lines. So if you look at the tangent lines to those circles, then you can measure the angle. And orthogonal means that that angle is 90 degrees. Okay, does that make sense? So given any 2 points, there exists, in fact, a unique line. By line, now I mean arc of a circle that meets the boundary, the salami. What is salami? The casing. The casing of I'm going with it. The casing will be met at a right angle by this arc. Okay. P2. What's P2? If you already have a line segment, you can extend it. Yeah. So the segment, of course, is just a little bit. If I have 2 points, so here's the whole line will be like this, but the line segment will be something like that. And given a line segment, can I continue that circular arc? Yeah, no problem. This is continue line segment a little further, if need be. Postulate 3. Yeah, draw a circle. Yeah, postulate 3 is draw a circle. Draw a circle. This gets a little harder because I have to explain to you what distance means in this geometry, but there are indeed circles. So trust me that this can be done. And postulate 4. Which one's postulate 4? You remember? It's the one about right angles. All right angles are equal to all others. All right angles are equal. Well, that still holds here. Right angles. So what is a right angle? It's when 2 circular arcs intersect in such a way that the angles, adjacent angles, are equal in the same exact way as before. Okay, so this is a geometry that satisfies all 4 of these conditions. But now let's think about postulate 5. So before we get to postulate 5, let's get to know this geometry a little bit. And here's a great way to get to know this geometry because it was rediscovered completely independently by, has anyone heard of MC Escher? Yes, yes. The staircases, here are the staircases and the birds turning into, the pattern down here and relativity and waterfall and all kinds of great stuff. And if you look at Escher circle limit, so here are a bunch of his circle limits. Let's grab, this is a good one. Okay. No, just give me Wikipedia. Which one is this? This is, come on. All right, this is a good one too. All right, I want to grab this one. I'm just going to show image. Okay, there we go. Now I can zoom way in. Okay, what is going on here? In fact, let me just copy this image. Copy image, and let's paste it into here and mess with it. Sorry, Escher. They're notoriously, they don't like anyone using their stuff, even though it's from 1958 or something. You can't get permission to, so hopefully we won't get sued. Hey, it's fair use, right? Education, it takes a second to paste it in for some reason. So Escher was not a mathematician. Escher had a long-running correspondence with a famous mathematician named Coxeter. Did it paste? Hello? Pretty please? You have to ask politely. Does anybody see where it pasted? It thought for a while that was good, and then it disappeared. Okay, let's try again. Paste. It pasted a tiny version, but that's okay. There we go. Okay. Okay, so here we go. And did I end up rotating it a little bit? I don't think I did. Boom. All right. This is Escher MC Escher. You can where is his signature? I don't see it on this. This is a circle limit, one of his circle limits. I believe this one's from 1958. He's not a mathematician. He's an artist. He's just messing around with forms and doing all kinds of crazy things. He has a long-standing correspondence with a mathematician named Coxeter, a Canadian mathematician. But their letters are like, Escher sends him a picture and Coxeter writes back a really long letter explaining what's going on. And Escher says, that's nice. I didn't understand anything you said, but here's another picture. And just like they go back and forth for a while. So what's going on here? Ooh, very good. Okay, so let me show you what's really going on. And for that, I have this movie that a friend of mine made. Okay. These are three geometries. What is happening in the middle? Euclidean flat space, right? This is a little 30, 60, 90 tile that you put on your bathroom floor, and you have to turn it over and it'll just tile the entire plane as far as you want. We can't see the whole plane, of course. We're only seeing a little bit of the plane, but we see straight lines as straight lines. We see the angles as 30, 60, 90, exactly as they are in real life in the geometry. What's going on the left? On the left. Emily.
Is that like spherical geometry?
Yes.
So wait, is spherical geometry like the same thing as projective geometry?
So they're slightly different. Spherical geometry is just the geometry of the sphere. When we want to use the sphere as a model for synthetic geometry, for geometry where point slides and planes are things that are supposed to satisfy those original axioms, we have to, if two lines are supposed to meet at a point, we have to change our meaning of the word point. So that's the subtle difference between projective geometry and spherical geometry. Never mind right now, just tell me what you see on the left. Yeah, it's a 3D sphere that's just moving around, right? Of course, that's not what it is. It's just a flat piece of whatever this is made out of, right? It's just projection of a screen. But your brain has had so much experience with looking at spheres that it has no trouble taking that thing and just forcing it to be 3D in your mind. You have so much experience with this that it looks 3D to you, even though it's flat. It's a projection. It's not, these are not straight lines, right? They're curves, but you know that if you were to look at the sphere, if you really like line it up and look at it, you would see a straight line. And these are angles, and the angles, like this is the wrong, if I pause it somewhere, pause it please. Okay, like this angle locally, if I zoom in, I don't think I can't zoom in. If I zoom in, this angle is supposed to be the same as that angle, which is like 60 degrees, but that doesn't look like 60 degrees. That looks like a lot less. This angle is a lot more than 60 degrees. That projection does not respect angles. It does not respect lengths either. This length looks much longer than that length, even though they're supposed to be the same. And you can imagine cutting out one of these tiles. This tile, it turns out, this is a 90-degree angle. How can I tell that that's a 90-degree angle? Yeah, zooming in, if you just count around this vertex, around this corner, if you count how many tiles there are, there's 1, 2, 3, 4 tiles. All the tiles are supposed to be the same. And so if you're going to get 4 things to go around 360 degrees, each of them had better be 90. How about right here? How about at this dot? What's the angle? What's the angle in this corner? How'd you get that? Yes, exactly right, Danielle. Exactly right. If there's 5 black and 5 white triangles all meeting at this corner, they all have to be exactly the same. So there's 360 degrees getting divided among 10 corners, 10 angles coming in. So each one of them had better be 36 degrees. So this is a 90-degree angle, a 36-degree angle, and how about over here? 60. So this is not a 30, 60, 90 triangle. It's a 36, 60, 90 triangle, because on a sphere, triangles add up, the angles on a triangle add up to more than 180 degrees. So this is a little bit more. And if you were to make that thing, that tile, you could take that tile and flop it around and make a sphere out of it. Okay, a real sphere, genuine sphere. What's happening on the right is exactly the same thing, just in hyperbolic space. Let's look at the triangles. So what is, let's look at this corner. Okay, so we're gonna look at one of these triangles. Here's one of these tiles for the hyperbolic plane. What's amazing about hyperbolic space is that unlike spherical space, where we're only seeing the front of the sphere, right? We're not seeing the back. There's a whole other bit of it. We just can't see it in that projection. Here in the plane, we can't see the entire infinite plane. I don't have an infinite projector to show it to you. I can only show you ever a tiny piece of it. The amazing thing about this model of hyperbolic geometry is you see the entire hyperbolic space all in one fell swoop. This is it. This is everything. Okay, so you're seeing, you're not missing anything. There's nothing on a backside. There's no parts that have to get cut off. This is all of it. And the angles that you locally see in this model are correct. What's funny is that straight lines, what we mean by straight lines is what we said before. It's these arcs of circles where the arcs are orthogonal to the sausage's casing. Okay? And so let's look at one of these triangles. What's this triangle? What's the angle here? That's the hardest one. What is it? 30? Why do you say 30? Yes, there's 6 black and 6 white angles meeting here. So there's 12 of them total. 360 divided by 12. 36 divided by 12 is 3. So this is a 30-degree angle. Okay. And how about this angle here? 90. Everybody see that? You getting the hang of this? That's 90 because there's 4 things meeting here. So this is a 30, 90. Is that 60 or what is that? Can't be 60. Otherwise, we'd have Euclidean geometry. 1, 2, 3, 4, 5. It's also 30. It's a 30, 30, 90 triangle. Okay. The sum of the 3 angles have to add up to less than 180 degrees. And so I just want to show you the motion because you're familiar, please. You're familiar with the motion, as a circle rotates, and you're familiar with the motion as a plane slides around. And this is the same exact motion, just in hyperbolic space. It's slowly deforming around. Every single one of those lines is a straight line. And the angle that you see, the one that you would see from the projection, is the true angle in the geometry. There's no deformation of the angle. The lengths look like that looks like a tiny triangle, and this looks like a big triangle. That's a distortion. They're actually the same triangle. And completely independently of all of these, great mathematicians, this artist, Escher, comes along and says, yeah, I figured all that out. And so each of these, what are these, angels and devils or something? They're fish. So this is a black fish, white fish tiling. And each of these fish have exactly the same size in hyperbolic space. There's this big fish over there and that tiny fish over there, and they're the same size. It's just there's a distortion because of the projection. What is the fundamental tile? So here's a really fun thing to do. What's a tile of hyperbolic, something that'll fill up all of hyperbolic space that will make this image? So one way to look for the tiles is to look for symmetry. So here there's like every one of these lines is a line of symmetry of the image. And so where's the symmetry here? There's one easy symmetry, which is just the straight line. Why is that straight line a straight line in the geometry? What are straight lines in this geometry? You remember? Go ahead, Amelia. Yeah, they're circular arcs that are orthogonal to the boundary, that meet the boundary at a right angle. Well, is a straight line a circular arc? Yes. a straight line is a circle of radius infinity. So if you think about deforming this from you know, a little curve like this, well, let me draw one curve. Well, so here's a straight line of the kind that I described. That's a straight line in the geometry. And if you think of that straight line just kind of sliding over until it becomes this thing, it becomes an actual straight line in the projection, and then it continues and becomes this straight line, which is a line of symmetry. Cool. Here's another straight line, which is actually straight in the projection. And here's one more. And let's draw one more. How about here? Is anyone starting to see what's going on? I claim that this shape right here is a tile.
It's kind of the same shape as the fishes.
Yes. It's a quadrilateral. And as you move that quadrilateral around, you get everything in that direction. As you move it from here to here to here to here to here to here, you get the same tile. But then as you take this same tile and you move it down there, you get the same tile and the same tile and so on. Amelia.
It's how the Escher, like, he drew the lines that you're drawing.
Yes.
That's like crazy.
Yes.
And, like,
He
didn't
completely-
care about math at all, and he just.
Yeah. He was doing all kinds of crazy stuff. Right? He draws the Mobius band, he draws his hand, drawing his hand. He draws a self-portrait of himself looking at a spherical globe. He's an amazing, amazing artist. He completely independently discovered this thing that mathematicians 100 years before were trying to make sense of.
How should we like imagine the disk? Because it looks kind of like a bowl, like you're almost looking into something concave, and like the middle image is the like it appears to be the largest. How should we imagine this?
Yeah, it's really hard to think of it in terms of anything that you know, because if you actually want to see, okay, so here's one. I hesitate to say this because I don't think it's actually a good way of thinking about it, but geometrically what's happening is that at any point in hyperbolic space, it looks kind of like a horse's saddle. So in flat space, near any point, you just see like a plane. In spherical space, this is called positive curvature. Near any point, you see what looks like a cup, right? Whichever way it's facing. Near a point in hyperbolic space, what it looks like is a saddle. So there's one direction where the curvature locally is pointing down, and another direction where it's pointing up. And it's this clash of directions that gives it that structure. It turns out that there's no way people will crochet hyperbolic hats or something. I don't know if you actually can wear these things. But once you get out a certain distance, it starts to crash in on itself. There's actually no way. In fact, if you actually to do it correctly, infinitesimally it will crash in on itself. The second you move any distance away from a point, and you try to realize hyperbolic geometry in R3 in Euclidean space, it's not going to work. So that's why it's better to think in the model. Actually, I do a lot of thinking about hyperbolic space, and I do it all in the model where I can draw something. Anyway, I just wanted to show you this so you get an impression for what the kind of geometry is that Beltrami discovered. And he gave a model. This is what I'm showing you is Poincare's model. Never mind, Beltrami's model is very, very similar. It's often called the Klein model for reasons. But it satisfies all four of the original axioms in the correct interpretation of the words point, line, and plane. Obvious. Yes, that's what it eventually became known as. Yes. It's much more complicated than that. There's a famous line of Einstein's, don't worry about your difficulties with mathematics. I assure you mine are still greater. There's like a girl that comes to him and says, I have trouble in school math. And he says, you're struggling with math. I'm struggling with math too, I promise you. And it's because he's trying to learn Riemannian geometry. And Riemannian geometry, these are all constant curvature spaces, the flat plane, the round sphere, and this like perfect hyperbolic geometry. And what Einstein has to understand is variable curvature. And the space-time is curved by the presence of matter. And that curvature is not, it is in space-time, in this four-dimensional space-time, is the way it gets bent is what it is, this saddle type bending.
So there's just, we can't like really, so we just like can't really imagine it. We just have to like know.
You start to get an intuition for it when you play with it long enough. The reason this picture on the left makes so much sense to you is because your brain has had 18 years of experience with looking at spheres and knowing that you know how kids love peekaboo? It's because when you're not there, they're like, you're gone. And then you appear again and they're like, oh my God, there's a person again, right? They don't know that there's like something behind the hands yet. And then over time, they're like, oh no, you're really still there. This game's no fun because you're just covering your face and I know you're there. So your brain has had decades to think about the fact that there's a backside to this sphere. And you know that what you're looking at is just a projection. Anyway, your eyes ever only see 2D. It's the fact that you have two of them and you get a little parallax when you move around that lets you see, lets your brain tell you that you're seeing in 3 dimensions. You're never seeing in 3 dimensions. If you want to think about that. Any one eye can only get a plane's worth of information. So the fact that you have 2 of them and that as you move around, things closer to you move faster than things farther from you. Yeah, that's called parallax. That's what allows to trick your brain into making you feel like you see 3D, but you don't. And in the same way, you've had 7 minutes of experience with thinking about hyperbolic space. And so it's this weird and crazy world that when you live with for a couple of decades, you're like, yeah, it's just, yeah, I have, you get intuition about what's going on. That's the thing. When you understand something, it's when you can predict what will happen to it. So you can predict what will happen if I turn this sphere a little bit, and what your model of what a sphere looks like says that when I turn it a little bit, it's going to change like this. And then you see it and you're like, yes, of course, that's what I expected. So you've had 7 minutes of experience with this, and maybe it's hard to see what you would expect here. But over time, I mean, if you continue studying this thing, the hyperbolic space is not on the quiz, right? This is just for fun. I'm just trying to explain something to you. Elisa, you got a question?
The additional reason why I think that the left is much easier for me, like the right's giving me a headache.
Yes,
But the
sorry
left
about
is
that.
Easier for me also because I feel that I've spent a lot of time like, if you want to like first, like, do you want to draw a soccer ball, or do you want to draw, like the fact that it's not only seeing in 3D, but attempting to draw in 3D.
Yeah.
And I haven't been like attempting to draw in hyperbolic.
Right.
But I think a lot of, I don't know, at least for myself, that if I ever wanted to, in any art class or in any like, you want to draw a picture for someone and you want to draw something in 3D, that's something that I'm attempting to work on. Now, I don't know if this is like regarding the peekaboo thing. I was trying to teach some young children like how to draw a box in 3D, and I think they can't do really struggling to grasp it. And I was like, oh, maybe they can't. I don't know if that's true. Maybe that's beyond the scope of this course. Like, I don't know.
Yeah,
This is easier for us, but if we had a 3-year-old in this room, I don't know if they're really struggling to grasp the square in 3D.
The way the brain works is a fascinating thing, and it takes time and sleep and like looking away from it and looking back at it again later for the neurons in your brain to start beating at some rhythm that recognizes patterns and predicts what you expect will happen next. And the more that's the case, and the less chaos there is, the more you can predict the result of an experiment, or the next word that I'm going to say, or what the next pixel image will look like. The more you do that, the more comfortable you become in something. So Yes, you're absolutely right. Actually, it's very funny that you mentioned that. Perspective drawing is something, again, that was discovered by artists before it was understood properly by mathematicians. And there's this great period. I don't know that we'll get to it, which is why I'll take a second to talk about it now. There's this great period in the 15th century, maybe 14th. I'm trying to remember. I think it's 15th century, where artists are starting to figure out how to draw properly in perspective, where if you have true parallel lines, like what do parallel lines look like in the real world? If you draw a scene with a railroad track, right? This is not how railroad tracks go in real life. They go like this to the horizon, to the point at infinity. But the point at infinity is there. It's like it's on the horizon, right? This is what parallel lines look like. And so there are these early. I'm not gonna be able to grab them in real time from the internet, but like this is an instance where artists were ahead of mathematicians. This is an instance here in hyperbolic geometry. Mathematicians understood this geometry, and Escher sort of rediscovered it and did all kinds of beautiful things with it, which is why I'm pointing to Escher. But in the case of drawing in perspective, artists understood that, and later mathematicians came along and proved the theorems that recognized what was happening.
This is like, well, this was pretty recent, but like the golden ratio in art was just like mathematicalized. Like some mathematicians or somebody did something where it's like, it's most pleasing to look at a painting when it's in perfect thirds. And then like, I just saw a lot of artists respond and they were like, yeah, we know, like we've been doing this. But yeah, it's like the same thing.
Yeah, the golden ratio is it's a controversial one. Let me but you're absolutely right. That's something that people think they find aesthetically pleasing, like the aspect ratio of this thing and this thing is some maybe could be close to the golden ratio. We can come back to that topic. I just want to make sure that I finish off. So what that we have this other model. Why does that mean that you can't prove the parallel postulate? How does Beltrami finish the argument? Once he realizes the role of models, discovers this alternate model for hyperbolic geometry. Amelia. Yes, absolutely. So what? Yes, the fifth postulate is not true. Yeah, let's anchor that. Let's drive that point home. If I have a line and a point not on that line, how many parallel lines are there? What's a parallel line? It's a line that does not, in the same plane, that does not intersect the given line. How many parallel lines are there to this line that they don't cross, that go through that point? Well, here's one. That's supposed to be a right angle. And here's another one. Still doesn't cross the first line that I drew. And here's another one. Okay, you see there's infinitely many. In fact, uncountably many. We'll get to uncountability. So there's infinitely many parallel lines to the given line. And remember we tried to draw the square by just taking two right angles? And then, or I guess three right turns, going a certain distance and taking three right turns. And that doesn't work on the sphere. It doesn't work in hyperbolic geometry either. Okay, so there is no square in hyperbolic geometry. It's not possible to make a square in hyperbolic geometry with, all angles 90 degrees and all side lengths the same. Doesn't exist. Amelia. Alexandra.
They not meet at any point if they go around the sphere?
Well, this isn't the sphere. This is the disk. This is the salami slice. Sorry. This was meant to be the hyperbolic disk, as opposed to the sphere model. It's hard to tell the difference when both are being projected.
Okay, good.
Yeah. Okay, so what's the conclusion of this? Having given this model, how does Beltrami conclude that the parallel postulate cannot be proved from the other four? This is a very subtle idea. We're so close to it, but it's still, I claim it's still a leap of understanding to cross this threshold.
Because the
other classes are only working in Euclidean geometry, and it's the acceptance that for the entire book, you have to be staying in this world. Whereas if you start to move and start to prove it, it's actually not provable because then you start considering these other claims. That was a lot of words. I have the picture in my head. I don't
Yeah.
know.
I think you're very close to the idea. I guess the way I would put it is any fact, let me say it first. Any fact in Euclidean geometry is also a fact in hyperbolic geometry when you reinterpret the words point, line, plane, circle. Anything that's true, any fact in Euclidean geometry is also a fact in hyperbolic geometry. This is what once we geometry, just with the words, the undefined terms, point, line, and plane, and circle, point, line, circle, plane, plane, being redefined, being shuffled around, being shuffled around from one model to the other, shuffled around from one model to the other. So if you're trying to find a contradiction by assuming P1 through P4, any theorem that you're trying to prove in hyperbolic space and trying to get to a contradiction will be a theorem in Euclidean geometry. Just instead of saying two lines intersect, you'll say two circular arcs intersect. You can state any theorem in Euclidean geometry, any theorem in hyperbolic geometry as some other theorem in Euclidean geometry. And so they're mutually consistent with one another. In other words, any contradiction in Euclidean geometry, any contradiction in hyperbolic geometry will also be a contradiction in Euclidean geometry. So any potential contradiction in hyperbolic geometry will have a corresponding statement. Any like theorem that you prove that you arrive at 1 = 0 or some nonsense has a corresponding statement in Euclidean geometry that is also a contradiction. That's the final, that's nail in the coffin. That's the final idea, is that you can move from one model to another. And so if you're going to assume that the parallel postulate is false, we have postulates 1 through 4. If we assume the fifth postulate is false and we come up with a contradiction, that contradiction will be a statement in Euclidean geometry involving circles instead of lines that will also arrive at a contradiction. And so the idea of models allows you to transfer logical statements from one model to another and conclude that you can't prove the parallel postulate. So it's not possible. So the models are just as valid. So it's not possible to prove P5. Again, now this is something that people have already said, since it's not satisfied, since it's not true in hyperbolic space, since it's not true in hyperbolic geometry, in the hyperbolic plane, while being true. While P1 through P4 are. Okay, does that make sense?
So are you saying, like, you're saying that this is the only contradiction, or you're saying every statement is a contradiction?
So let's go back to what we were trying to do. People were saying, okay, we agree with P1 through postulates 1 through 4, very simple, there's no problem. We all agree that those are postulates that should be kept in anything resembling geometry. Postulate 5 is a mouthful. Do you really need it, or can you prove it from the other 4? So let's assume that postulate 5 fails and start proving all kinds of consequences, deriving consequences of that. And if one of the consequences is a contradiction, is something that's like impossible, then we'll prove that the failure of postulate 5 leads to a contradiction. Therefore, postulate 5 is not an axiom, but is actually a theorem that you can derive from the other 4. Does that make sense?
I'm thinking
Like-
like this distinction between theorem or postulate?
Yes. So postulate, remember from the very beginning, people realized that postulate is another word for axiom. Postulate and axiom are the same word. And proposition and theorem are the same word. Unfortunately, the old-fashioned thing is to use postulates and propositions, which both start with P and cause confusion, as opposed to axiom, which is like, these are the things that we'll take for granted. We hold these things to be self-evident. We hold these truths. An axiom is a truth, right? So you start with axioms, and any math starts with axioms, and then you try to derive consequences of those theorems. And you prove another consequence, another theorem, and you prove another consequence, another theorem. And maybe you prove another fact, but you know that fact is false. Let's say you prove a fact that's just not true. Well, then what's wrong? As long as your logic was okay, then this axiom must have been wrong. And your starting point must have been wrong. Okay, so they say, let's say we take P1 through P4, and in addition to P1 through P4, we'll take the failure of P5. This is the mathematical symbol for not. Okay, so this is not P5. For example, in hyperbolic space, P5 does not hold.
But it still holds in like Euclidean geometry?
Sure, yeah. The question is, do we really need to assume P5 in order to do Euclidean geometry? And so the question is, well, could there be some chain of theorems that arrives at a contradiction, at a wrong fact, a fact that we know is not right? If that were the case, then we would recurse all the way back and say, assuming the failure of the parallel postulate gives rise to a contradiction, therefore, it can't be the case that not P5 holds. Therefore, P5 must hold. Does that make sense? It's like a double negative. And what Beltrami shows is that any chain of logic in hyperbolic geometry has a corresponding chain of logic in Euclidean geometry, just with the words point, line, plane, circle, interchanging what their meaning is in the model. So you're not going to come up with a new contradiction that wasn't already a contradiction in Euclidean space. That postulate P5, we should be agnostic to. This is what we said in the video, if you remember. What this means is that you get to choose which video game you want to play. You want to play chess on just a regular board, or you want to play chess where the two sides are identified, chess on a torus, if you know what I mean. Anyway, it's like you get to choose which flavor of geometry you want to play, and they're all equally valid, and they have completely different truths. What is true in hyperbolic geometry is not true in Euclidean geometry. When you look at statements about what it says about lines or triangles or circles, some of the angles in a triangle is less than 180 in hyperbolic space, but equal to 180 in Euclidean space. Right? Those are different facts, but that's because of this different interpretation of what the core objects are. Josie. No, I'm saying that you can't prove P5 from P1 through P4 because there's a model where P5 holds, namely Euclidean space, and there's another model equally logic without any new logical contradictions from Euclidean geometry where P5 does not hold. Cindy.
Explain what's going on. So
Please.
imagine to be a valid university, you need to have first axiom is you need to have majors. The second axiom is you need to have certificates. And the third axiom is that you need to have a thesis. And what we basically did was we looked at a lot of the different universities, like also to Princeton, and we said, oh, well, other places have their own version of a concentration. They just don't call it that. Or they also have certificates. They just don't call it that.
Right.
But then not everyone needs to have a thesis to be considered a valid university. Like, and we're not wrong. They're not wrong. It's just a different kind of university. But the major and minor thing is not negotiable.
Yeah. Does everybody follow that? I like that example. Okay. Other questions? I think that's all I wanted to tell you about models. Is there anything else I wanted to tell you about models? No, I think we can go on. All right, so that's book 1. We have 13. We're not going to obviously not going to spend the rest of our days just going through Euclid's elements. Let's have a glance at what's in some of the others. Let's see, Euclid elements. Here we are. Let's look at book 2. So book 2 starts. I think I mentioned this last time. Book 2 is like at least at the beginning is like algebraic proofs or geometric proofs of things like a squared, a plus b quantity squared is a squared plus 2ab plus b squared. Let me just show you where that is literally. The first couple are kind of boring. Is this the one? That one's a little too complicated. That one's also a little too complicated. Maybe it's 4. Yeah, here we go. Okay. So this literally is book 2, proposition 4. Book 2 of things like proposition 4. Proposition 4, the book is 2. And what's the proof? Let's just look at the statement. If a straight line is cut at random, then the square on the whole equals the sum of the squares on the segments plus twice the rectangle contained by the segments. Thank God we have algebra. The amount of brain power it takes to parse this sentence takes away from the brain power you have to analyze what you're trying to do. Okay, so let's look at the statement. Let the straight line AB, so AB is a line segment, be cut at random at C. I say that the square on AB, in other words, if you make the area, if you make AB into a square, equals the sum of the squares on AC. There's the square on AC plus twice the rectangle on AC by CB plus the square on CB. Okay, A plus B quantity squared is A squared plus B squared plus 2AB. Thank God for algebra. Okay, we don't need to go through the proof of this. I'm just showing you that it's there. Who's the big boss? Every book has a big boss. Proposition 14 is the last one. Proposition 14 is the end of book 2. What is it? Don't even read it. Just look at the picture. Squaring a rectangle. Squaring a rectangle. To construct a square equal to a given rectilinear figure. Okay, so you already know this. Quadrature of the rectangle. That's the big boss of book 2. So book 2 builds up to that. Let's skip ahead. Book 3. What do we got in book 3? Book 3. Okay, a couple of definitions. Now we get into circles to find the center of a circle. Okay, so let's it's always nice to look at the beginning to get a sense for what's going on, and then we look at the end. Find the center of a circle. So book 3 in general is about circles, tangents, all kinds of good stuff. I don't know what happened here. So proposition 1, so proposition 3.1 is to find the center of a circle. Okay, what's the idea? Somebody drew you a circle and forgot to tell you where the center was. Let's say I drew the circle, but I didn't mark where the center was. And find the center. What are you going to do? So think about what it means. I can certainly draw 2 points on a circle, right? I can just put a point on the circle. The center is going to be equidistant to those 2 points. What is the set of all things equidistant between 2 points? If I give you 2 points and I want the locus of all points that have the same distance to these 2. Anybody know what that is? It's the perpendicular bisector. If I take the perpendicular bisector, then any point on the bisector has the same distance to here as to here. And this is another point on the bisector, has the same distance to here as to there. Right? Because you're making an equilateral triangle. An not equilateral, sorry, an isosceles triangle. An isosceles triangle has a altitude that splits the base in half. So what should you do with that hint? Yep. And then you bisect it. Okay. You bisect it. Well, the center's somewhere on here, but where? Amelia. Yeah. Take another pair of points and do its perpendicular bisector. That's a perfectly good solution. And then that point is the center. That's actually not what Euclid does. It's very close. The first step is the same. I love your second step. Here's what his second step is. What do you do? So you're given ABC. ABC are 3 points on the circle. He says, draw the straight line from A to B and bisect it and draw a right angle. So that's the bisector. And then he says, well, this new bisector will have 2 points of intersection. Take the midpoint. The midpoint of those two points of intersection is also the circle. We're not going over these in any detail. I just want you to know kind of what's in there. It gets juicy when we get to the end of book 3. So who's the big boss at the end of book 3? All the way down, proposition. It's actually 36. 36 is the big boss. I'm not even going to write it down. It's the modern name for this is a power of a point theorem. Yeah, I'll write it down. I'll tell you what 36 is. Just because it has the same structure as book 1, this ending. So prop book 3, point 36, the modern name is power of a point. But what the theorem really says is if you have a circle and you have a point outside the circle, I'm not even going to give these things names. Don't bother writing this down. I just want you to kind of hear it. If you have a tangent line, so I'll give these names. Okay, so this is like D and this is maybe A, and then I cut any secant, just a random secant, B and C. Maybe Euclid's goes through the center, but there's no reason to go through the center, okay? So DBC is just any, secant means you just cut it at random. It's not necessarily a diameter, it's not a radius, it's not tangent. But AD, I assume, is tangent. So one way of knowing that something is tangent is that it's orthogonal to a radius, okay? And the theorem is that if you take the length of DB and you multiply it by the length of DC, does anybody know what you get? Did you study this theorem in high school geometry? It's the same thing. It's invariant. It doesn't matter which secant you take, that product will always be the same. In particular, if you think of pulling this secant like somewhere else, you can pull it there, you can pull it there, you always get these 2 points, and you multiply the two lengths and you get the same thing. You could pull it all the way until those 2 points come to a single point, and that single point is A, and then you'll get dA squared, dA by dA. Okay, so that's called the power of a point theorem. Let me just show you what it looks like in Euclid. Again, don't read this. It's impossible to parse, but just look at what he says. Let D be a point taken outside of a circle ABC, and let D, the straight lines DCA and DB fall on the circle, and let DCA cut the circle. So DCA just is a secant, and let BD touch it. So BD is tangent to it. I say that the rectangle, that he has to construct a rectangle. He doesn't know how to multiply. He's constructing a rectangle. The rectangle AD by DC, so that's the long secant length by the shorter secant length, is equal to the square on DB, which is exactly what we said. Okay, what do you think prop 37 is? The converse. Very good. Prop 37 is the exact opposite, as is the converse. If, again, you have the same setup, and assume that the rectangle AD by DC is equal to the square on DB, then DB is tangent to the circle. So that's the converse. Again, don't bother writing these things down. I'm just want to show you some of what's going on. Okay, we're up to book 4. Now it gets really juicy. Book 4 begins. So book 4, yeah, let's go straight to book 4. I'll just record here. Prop 337 is the converse. If this relationship dB times DC is equal to dA squared holds, then dA is tangent. It's tangent. Circle. I'll just record that for fun. Okay, we're up to book 4. And book 4 does things like inscribe a circle in a triangle, circumscribe a circle in a triangle, right here, proposition 4, to inscribe a circle in a triangle, right? You want to draw the incircle of a triangle. These you probably saw in school, I assume. Inscribe a circle, inscribe a circle, circumscribe a circle, dot, dot, dot. It gets really good at the big boss. The big boss is prop 16, to inscribe in a circle an equilateral and equiangular 15-angled rectilinear figure. He constructs the 15-gon. That's the big boss. Prop 16, the big boss. You know what I mean, right? Is you play video games, at the end of like a level, there's always the bad guy that you got to defeat. This is what you're building up to. All that skill that you've built up is to be able to do Prop 16, construct, of course, with straight edge and compass, the 15-gon. Okay, he's very proud of this. And this is a fascinating story. Another one of the fascinating stories in the history of mathematics. Hopefully I can tell it in 10 minutes. So let's go back. How about the 3-gon? Where does he construct the 3-gon? Regular 3-gon. These are all regular. Book 1, proposition 1, right from the very beginning, he constructs equilateral triangle. When does he construct a 4-gon? Also book 1, just before the proof of the Pythagorean theorem. Yeah, it's I-46. Pythagorean theorem is I-47. The converse is I-48. Okay, so the 4-gon, also known as the square, and the 3-gon, also known as the equilateral triangle, he constructs, this is in I.1, this is I.46. The 5-gon he constructs just before. This is the hexagon. Here we go, prop 13. A circle, inscribe in a circle, a given equilateral and equally angular pentagon. Which is closely related to the golden mean, actually. The fact that the golden mean is a quadratic irrational means that the pentagon is constructible. So the 5-gon is constructed in book 4, proposition, what did we say? 13. Okay, so that's in a circle, you can construct a regular, this is my attempt at a regular pentagon. How about a hexagon? Right here. I-15. So this is in the same book 4. 15 constructs the hexagon. How does he construct a hexagon? How do you construct a hexagon? Any ideas? Yeah, you can make an equilateral triangle. And so you can make the center of the circle. And so this angle, what's this angle? Close, 180 is all the way open. We have to divide the entire circle into 3. 120. Yep, that's 120 degrees, which actually it's easier to think about as 2 pi over 3, right? 2 pi is the whole circle and divided by 3 because it's a 3-gon, regular 3-gon. Does that make sense? Everybody with me? So all you have to do if you want to make a 6-gon, yes, exactly, Josie. Bisect. We know how to bisect angles, right? We can make a 6-gon by bisecting this angle. And so if I bisect 120 degrees, I'll get 60 degrees, which is what I need for a hexagon. Okay, 60 degrees, which is 2 pi over 6. Pi over 3. But it's better to think about it as 2 pi over 6, right? So that gets me that point. And of course, I can copy an angle, and then I get a regular. Hopefully, I've drawn something approximating a hexagon. Okay. So 15, he constructs the hexagon. Prop 16, he skips straight to the 15-gon. 15-gon is the very next thing. And the last thing of the book, of book 4. Why doesn't he construct a regular 7-gon? He doesn't know how. It turns out that you're absolutely right. It turns out it's not possible. How about an 8-gon, octagon? Can you do an octagon? Not in a triangle. In a square. You take a square. A square has this central angle, which is 90 degrees. You bisect that, and there's your perfect octagon. You can make a pizza. Right? Pizza's cut into, this is meant to be an octagon. Right? So in fact, by bisecting, I'll come back to how he does the 15-gon. By bisecting, you can make, I'm supposed to be writing not in chicken, but hopefully you can read this. You can make the 3-gon, the 6-gon, the 12-gon, the 24-gon, and so on. You can make any power of 2 times 3. You can make a 2 to the n times 3-gon. You can start with a square, a 4-gon, and it's a 4-gon conclusion that you can make any 2 to the n-gon. Sorry. Should have stuck with salami. He can make the 5-gon. So you can make a 10, 20, 40-gon, and so on. Any 5 times 2 to the n-gon. How does he make a 15-gon? This is a little subtle. Let's just think about the angles. He knows how to make a 5-gon. 1, 2, 3, 4, 5. There's my pentagon. So what is this angle? 2 pi over 5. 2 pi over 5, no problem. Okay. He also knows how to make a triangle, an equilateral triangle. And what is this angle?
2 pi over 3.
Yes. And so what is this angle? Let me pull this all the way to here. It's the big 2 pi over 3. This whole 2 pi over 3, or someone was about to say? Amelia? Well, what's the big angle? 2 pi over 3. And what's this angle that we're taking away in order to make the new angle? 2 pi over 5. So I can pull out a 2 pi. What's a third minus a fifth? 5/15 minus 3/15? 2/15, which is almost what I want. I have this new angle. All I have to do is take this new angle and bisect it. And we know how to bisect angles. And this angle will be, yeah, 2 pi over 15, 1 over 15, 1/15 of a circle. Okay, so it's no mystery that we can make a 15-gon. So we can make a 15-gon, so we can make a 30-gon, so we can make a 60-gon. Oh, that's cool. We can make a 60-gon. 60-gon is constructible. 120-gon and so on. 15 times 2 to the n. And this is all that was known for 2,000 years. These constructions of regular n-gons were the only ones known for 2,000 years. As we said, this is not a book that languished in obscurity. Every reasonable scientist of any worth read this. The Arabic scientists, the Indian scientists, Chinese scientists. This thing was scattered across the globe. And that's all anybody knew. Some of you are 19, some 19-year-old kid in 1796, a 19-year-old kid by the name, what is it? It is Gauss. It's Carl Friedrich Gauss, by the name of Gauss, is a nobody. Nobody knows who he is. Discovers that the 17-gon, is constructible. He is instantly world famous, because this is something that, like, a lot of people would have liked to know that this is possible, why this is true. And it re-energizes people into start thinking about constructibility. And this is why I say Gauss leads into Wansel and the non-constructibility of the triangle and the doubling of the cube. So what he really discovers is even more spectacular. The reason the 17-gon is constructible. And of course, once you can construct the 17-gon, you can do the same trick to make a 3 times 17-gon, or a 5 times 17-gon, or a 3 times 5 times 17-gon, or doubles of any of those. So let's just focus on the 17-gon itself. The reason the 17-gon is constructible is that 17 is 16 plus 1. And notice that 3 is 2 plus 1, and 5 is 4 plus 1. And 16 and 4 and 2 are all powers of 2. And what he really proves, Gauss's theorem, is that the n-gon for prime n, for n prime, is constructible if and only if n is a Fermat prime, what's called a Fermat prime. So I have to tell you what Fermat discovered. This is now, we're jumping centuries. This is 1630s. 1630s discovered that 2 to the n plus 1 can only be prime, can only have a chance of being prime, if n itself is a power of 2. So really, 2 to the you can't read this. You have to do it in 2 to the something plus 1 is what's now called a Fermat prime. And in fact, Fermat believed that all of these numbers are prime. It turns out only the very few of them are prime, and we believe that eventually this list is, well, we don't really know, but there's evidence that this list will eventually only be composites. But so 1 plus 2 to the 2 to the 0. What's 2 to the 0? 1. 2 to the 1 plus 1 is 3. How about 1 plus 2 to the 2 to the 1? 2 to the 1, 2 squared plus 1. And 1 plus 2 to the 2 to the 3, 2 to the 3. I've done something wrong, and I don't know what it is. We're supposed to be getting 2 to the 4. Oh, I missed. That's what I did wrong. That's the next one. I'm skipping ahead. 0, 1, 2 is how you count numbers in English. 2 squared, 4, 2 to the 4, 16. 2 to the 4 is 16. It's okay. It's 16 plus 1 is 17, and it turns out the next one's also prime. 2 to the 8. 2 to the 8. 2 to the 8 is 1024, 512, 256 plus 1 is 257. Wait, 257 is prime? I don't think it is, actually. I think it's the next one. 2 to the... Okay, anyway. So he shows that Fermat primes are the only n-gons for which the n-gon is constructible. 7 is not one more than a power of 2, so the 7-gon is not constructible. Amelia, then Laurie. Is prime? Thank you. Good. So that's the next one that's constructible. And how about the one after? 1 plus 2 to the 2 to the 4? What does Google say? 2 to the 16 plus 1? Yes? These numbers get very big very quickly. Is prime. Okay, so these are the constructible primes. You can take products of these and you'll get regular n-gons that are constructible. You can double them, you get regular n-gons that are constructible. And that's it. And that's all that you will ever get by Gauss's theorem. So Gauss completely puts to bed. Euclid opens the question, but nobody is able to walk through the door until Gauss, 2,000 years later, showing that these are the only ones that are